Fine.
Hello everyone, my name is Mohammadreza and today I'm going to present my work which is on Meta-Laminar jamming actuators fabricated by 4D printing. So through my PhD, I work on design and modeling of smart soft actuators which would be sustainable and they are kind of like composite actuator. But first, if we want to know what is actuators, we should know what is soft robotic. So soft robotic is a subfield of robotic that most of them are inspired by nature. So they are soft. They usually we use elastomer or silicone in these kind of systems, and they made of actuators, sensors, energy sources, and interface. So a combination of these components can make a robot to walk, crawl, twist, or other function that we need to do. But my main work during my PhD was on actuators and soft actuators. And in this this is one of my part. This one is a part of my PhD, which is on laminar jamming actuators. So, what is laminar jamming actuators? It's a composite actuator which consists of the different parts and layers, which they are inserted inside a vacuum sealing bag as you can see here. So these actuators can be activated through negative air pressure. So as long as we apply a negative air pressure, there would be a friction between these layers inside the jamming actuator, and until these parts are locked together and they perform a test based on design, so they can contract or bend throughout the whole system. So one of the biggest advantages of jamming actuator over rigid robot, they are safer and also more adaptable due to the softness that their nature have. So, what would be the biggest challenge in laminar jamming actuator is that sometimes if we want to do a long-term task, as an example, hold the product for 2 hours, we require the significant of air power to hold the actuator in a required position. So in this work, we have tried to reduce the energy consumption that comes from a vacuum vacuum pump. So the aim was a combination of 4D printing and laminar jamming technology to produce soft hard MLJ actuators. So these actuators do not require any continuous negative air pressure, and also they could consume less energy compared to the traditional laminar jamming actuator. And also the feature that they have is shape recovery, shape locking, and also holding with zero input power. So the concept start by which is well known by 4D printing. So we have an original shape. We heat the structure and the core structure. It goes to the rubbery phase, which is beyond glass transition temperature. Then we start vacuuming the actuator, and after we vacuum the actuator, we start to cooling down the actuator. So we would have two phase in these type of MLJ actuator. If we use PVC film, the actuator will bend. If we remove the PVC film, the actuator will contract. Then we just turn off the vacuum pump and start to heat the actuator. So the actuator goes back to its initial form. So we designed 4 different 2D lattices. So I tried to pick the popular ones among other lattice structures which widely have been used. So I 3D printed these lattice structure through FDM process. I use shape memory polyethylene material. Uh, then I just put the PVC film bottom of the core structure, put them into vacuum sealing bag, and finally I assembled the actuator using vacuum sealing tape. So these are the combination of manometer and also force gauge that I use to test the actuators. So before I test actuators, I've done test compression and fluctuate test. For compression, I wanted to see that with the less force, is the structure capable of to distribute force throughout the samples. or not. So as you can see here in circle 1, the applied force is just concentrated at the top of the structure, while the other type of the lattice can distribute the force totally all over the sample. So we tested the sample at room temperature and temperature beyond the glass transition. As you can see, the force drops sharply to 1 Newton because it goes to the glass transition shape. So this structure are like rubbery phase. And in Flexure test, I've done this test to see whether what would be happen if we put the structure inside the MLJ actuators and bend them. So I tested the structure without any sealing bag, and and also I used PVC film, which is unjammed at the left side, and the right side images are the MLJ actuators, which is jammed but without PVC actuator. So we tested all the samples at room temperature and beyond glass transition temperature. As you can see here, the force dropped sharply again, but when we jam the actuator, actually it shows that the structure and also the actuator become more stiffer compared to the rubbery phase because it is vacuumed, and also it has it requires much forces to bend the actuator. So after unloading, I measured the angle of the unloaded samples to see the performance of core structure when we unload them in terms of shape recovery. So overall, we decided to remove circle 1 because it didn't have it didn't have enough performance in terms of bending and also compression. So I've done the test on actuator. As you can see here, I tried the contraction and also bending through axatic and rectangle shape. When I increase the temperature, I start vacuuming the actuator, and also I cool it down the structure, as you can see in the thermal images. So they like the shape in the required position that we are willing to have, and then I just turn off the vacuum pump. They will be there. They will be in the position as long as we want. Then we just turn off the vacuum pump and start heating the actuator so it goes back to its initial form. As you can see, the image at the middle. So I've done tested on five samples. So I recorded the contraction, the tip bending angle, and also the shape recovery of actuators. So the tip bending angle, I drive the value from the Pasco software, and the shape recovery that was recorded through camera. So as you can see, we have a lens that when the actuator recovers its shape, we measure the length of the actuator at the end of the stage. So axatic has better performance compared to rectangle and diamond in this case. So we choose axatic structure and show it as a potential application in this research. So we start to heat the actuators. We just apply a deadlift to the actuator. We start heating it and turn on the vacuum pump. When it goes to the maximum contraction, we just turn off the vacuum pump and cool down the actuator. Then also we have the same thing in bending. So we use a 2D gripper, which can lift object and lock the shape as long as we want. So it helps to reduce the energy consumption that comes from vacuum pump, and also it can be in required position as long as you want. So the application of these smart actuators would be for sustainable actuators which can reduce the energy consumption. So it will help to grow the sustainability and also green design. So also we can use new materials and technologies to improve performance and efficiency of these robots. Also, we can improve the controllability of MLJ actuators since they are in earlier stage. And last but not the least, we can use these actuators in different applications like aerospace, automation, and robotic. Thank you.